Deep Learning Part 8, Attention and the Transformer. This is the finale, the architecture behind every large language model you have ever used. And here is the beautiful part, it is built entirely from the ideas in this course. Nothing new, just our familiar pieces arranged brilliantly. Let us assemble it. We begin with sequences. Language is a sequence, a sentence, words in order where the order carries meaning. And the dependencies reach far. The subject of a sentence can govern a verb 20 words later. A pronoun can refer to a noun long behind it. To understand any one word, a model must look at the right other words, wherever they happen to be. The old approach, read one word at a time, the recurrent network. It kept a hidden state, a running summary of everything seen so far. At each step it read the next word and updated that summary. Word by word carrying the past forward. For years this was how machines read text, but it hid two deep and fatal flaws. First, it is sequential. Each step must wait for the one before it, so it cannot be parallelized, and that makes it painfully slow to train. Second, its memory fades. Information from far back must survive through many updates, and just like a deep network's gradient, it tends to vanish. The long-range links, the very ones that matter, get lost. Attention throws out the bottleneck entirely. Instead of passing information step by step along a chain, it does something radical. It lets every word look directly at every other word, all at once. No chain to forward through, no memory to slowly fade. Each position simply gathers exactly the context it needs from anywhere in the sequence, in a single step. But how does a word decide what to look at? Think of it as a soft lookup. Each word issues a query, a question, what am I looking for? Each word also offers a key, an advertisement, this is what I contain. And a value, the actual content I will contribute if attended to. Query key value, a learned flexible retrieval. A word takes its query and matches it against every key in the sequence. The match is measured by a dot product. A large score means this query and that key align, this word is relevant, pay attention. A small score means ignore it. So every word scores its relevance to every other, a full grid of attention scores. Now turn those raw scores into weights. First, divide by the square root of the dimension, a small trick that keeps the numbers stable. Then apply the softmax. Scores of 2, 1, and 0.1 become weights of 0.66, 0.24, and 0.10. Positive and summing to exactly 1, a distribution of attention. Those weights decide the blend. Take each word's value vector and combine them, weighted by the attention. 66% of the first, 24 of the second, 10 of the third. And the result is a brand new representation of the word, enriched by exactly the context it chose to attend to. A word rewritten in light of its neighbors. When the queries, the keys, and the values all come from the same sequence, we call it self-attention. Every word rewrites itself in light of every other word. The pronoun finally finds its noun. The verb finds its subject. The ambiguous word finds the context that disambiguates it. All of it resolved in one parallel operation. And the whole operation is astonishingly compact. Pack the queries, the keys, and the values into 3 matrices. Then attention equals softmax of Q times K transpose divided by the square root of D all times V. One single line. A few matrix multiplies and a softmax. That is the beating heart of the transformer. Let us see it on 3 tokens, concretely. One token sends its query against all 3 keys. The scores come back 2, 1 and near 0. The softmax turns them into attention, 66, 24 and 10%. And the output is that exact blend of the 3 value vectors. Computed, concrete, and nothing but matrix arithmetic. But one attention is not enough. A word relates to others in many different ways at once: grammar, meaning, reference. So we run several attentions in parallel, we call them heads. Each head learns to attend to a different kind of relationship. One might track grammar, another meaning. Then their outputs are combined, many views merged into one. And here is the property that changed the world. There is no recurrence anywhere. Every word is processed at the same time, not one after another. The entire sequence flows through in parallel. And that is exactly what lets transformers train on oceans of text, on thousands of chips at once. Attention scales where recurrence simply could not. But that parallelism costs something. Attention by itself is blind to order. It sees a bag of words, not a sequence. To it the cat sat and sat the cat look identical. So we add position information directly into each word's representation. A positional encoding. Now the model knows not just which words, but in what order. Now wrap it all into a single repeatable unit, the transformer block. First, multi-head self-attention, to mix information across positions. Then a small feed-forward network, applied to each position. 2 sublayers. Mix across the words, then think about each word. That is the whole block. 2 familiar ideas hold that block together. A residual connection, it adds each sublayer's input back to its output, so the gradient flows straight through, deep stacks and all. The very cure for vanishing gradients from part 4. And layer normalization, to keep the activations well behaved from part 6. Old friends doing essential work. And look closely at that feed-forward network. What is it? It is just a small multi-layer perceptron, a linear layer, a nonlinearity, another linear layer. It is the very first network we built, back in part 2. Applied at every position. The transformer is not exotic, it is our familiar pieces, arranged with genius. Now stack the block. A dozen of them, 100, one atop the next. Each layer refines the representation, resolving more context, building more abstract meaning. Raw tokens enter at the bottom. And deep contextual understanding emerges at the top. That stack of blocks is the transformer. There are 2 main ways to arrange it. An encoder reads an entire input all at once, ideal for understanding. A decoder generates 1 token at a time, each one attending only to what came before, ideal for writing. Most large language models today are decoder only. Their single humble job predict the next token. So give that transformer one simple task, at enormous scale. Predict the next word. Feed it much of the written internet and train it with exactly the tools of this course. A forward pass, cross-entropy loss, backpropagation, gradient descent. And the result of that training is a large language model. And something remarkable happens along the way. Trained only to predict the next word, the model learns far more than spelling and grammar. It learns facts, translation, reasoning, the ability to write code. None of it was directly taught. It all emerged as the most efficient way to predict what comes next. And then the surprise that reshaped the entire field. Make the transformer bigger, more parameters, more data, more compute. And its ability keeps climbing smoothly and predictably. No new idea required. Just scale. From simple next word prediction, fluent language and reasoning and code simply emerged. And we can peer inside a trained transformer too. Look at its attention weights, and you can often see what it is doing. A word attending back to the noun it refers to. A verb attending to its subject. The grammar and the meaning of language laid bare as a grid of attention. Learned once again purely from the data. It is not without cost. Because every token attends to every other, the computation grows with the square of the sequence length. Double the context and you quadruple the work. Much of modern research is a hunt for cheaper attention. But the core idea, direct connections across the whole sequence, remains the foundation. An attention, like convolution before it, reaches beyond its origin. It now powers models of images, of audio, of protein structures, of many things at once. Wherever elements relate to distant, other elements, attention fits. It has become one of the most general and powerful building blocks we have. Now step all the way back. The largest models in the world are still exactly what we defined on the very first day. A differentiable parameterized function. Trained by minimizing a loss with gradients from backpropagation, followed downhill by gradient descent. Everything you have learned scaled up, nothing more. So let us recap not just this part, but the entire course. A network is a function, data defines a loss, backpropagation finds the gradient, descent minimizes it. Nonlinearity gives depth its power, regularization keeps it honest. Convolution reads images, and attention reads sequences. From a single humble neuron, a weighted sum, a bias, a squash. To the transformer, billions of those neurons, arranged to read and write human language. It is all the same handful of ideas, composed and scaled. There is no magic here, only function, loss, and gradient, understood deeply. And where does it go from here? Toward models that see, hear, and act, not just read. Toward agents that plan and use tools. Toward efficiency and understanding of why any of this works so well. But every step forward will still rest on the foundation we have built together in this course. You now understand deep learning not as magic but as machinery. The forward pass, the loss, the backward pass, the step downhill. Every model you will ever meet is some arrangement of these exact parts. You can see inside all of them now. And that understanding is yours to keep. So the whole course in one final breath. Deep learning is a differentiable function trained by gradient descent on a loss using gradients from backpropagation. From the neuron to the transformer, that is all of it. Thank you so much for watching and for thinking alongside me. Now go and build something.